Okay, good morning, everyone. Welcome to another session of Learning at Lambert Labs, and today's presenter is Tom Kobialka. So I'll hand over to Tom.
Yeah, thank you, Aaron. So today I'm going to be talking about the Slack outage, which occurred on January 4th, 2021, or as I like to call it, the Slackopocalypse. And I'm going to talk about kind of what actually happened and also about what could have been done to prevent it. So firstly, what outage are we talking about? Slack went down between 7 and 9:15 a.m. Pacific Standard Time on Monday, 4th of January 2021 for all users. And so obviously when this happened, people took to Twitter by storm. General kind of theme was, please hurry, please fix it quickly, please hurry. Some people were a bit more forgiving. Someone said, take your time. And one person even suggested perhaps that they should check their Docker version, if that might have caused the outage, but I'm pretty sure this person was joking. So before I move on any further, just a quick disclaimer, as I do not work for Slack, obviously, so I do not know what really happened. So I'm using two primary sources for this presentation. So one is the official root cause analysis report, which Slack published shortly after the incident. And they also wrote up a blog post where they also go into some detail about what happened. So before we look at the outage itself, we need to understand a bit about how Slack is built and how it works. So here is a very, very high level architecture diagram of Slack. So here on the left, we have the client, and on the right, we have our kind of backend services of Slack. And the way that Slack works is you log into the client, and the client sends a request to this web app backend here. And this backend returns a response, and the response contains kind of it's like a payload containing information about users, channels, which user is online, and that sort of thing. And it also returns a URL, and that URL sets up a connection between the client and the message server up here. And this is actually a Websocket, so it's a two-way real-time connection. And this means that you can receive messages without having to hit refresh. So that's what kind of makes Slack, real-time. RTM API stands for real-time messaging API. But that's like a very basic kind of overview of how Slack works. And the data is, of course, stored in the database here in MySQL. And these services are all kind of interconnected with each other. I also want to talk a bit about the growth of Slack. So Slack started, I think, in 2014, they were like properly public first time. In 2015, they had 2 million users, but by now it's over 12 million users. And also the number of organizations back then was 30,000, but now it's grown to over 750,000. So Slack has gone through quite a lot of growth during its time it's been live. Okay, so where is Slack hosted? So Slack is hosted on AWS. So when Slack started out, it had one AWS account, of course. But as there was growth in demand, Slack needed more resources to handle that growth. But more resources meant that one AWS account was not enough because of quota limits and so on. So Slack had to spread to multiple AWS accounts. And what they also decided to do, which is interesting, is they took their services and they segregated them into separate VPCs. Now, a VPC in AWS is a virtual private cloud. And the way they define it is it's a logically isolated virtual network. So what does that mean in practical terms? So when you go onto AWS for the first time, let's say, you have an AWS account, and you can access all the different AWS regions where you might want to, start a server. But before you can start anything in a region, you need to create a VPC first. VPC is where all the stuff you want to create goes into. And essentially, it's just like just an IP address, IP address space. So it's a space where you put stuff, and the instances can have their own kind of private IP address. So yeah, but that's kind of. I mean, if you were starting out on AWS, you might put everything in one VPC. There's no real reason not to. But it's interesting that Slack decided to separate all their services into different VPCs. So it will look something like this. So each service would be in its own VPC like that. Now, if services are segregated into logically isolated virtual networks, then how do they communicate with each other? So in other words, how can you tell AWS that the instances in two different VPCs should be able to communicate with each other? How do you tell AWS that? So there are various ways. So the first way is by something called Bpc Peering. So this is where you set up a network connection between two VPCs, and the instances talk to each other as if they were in the same VPC. So here we have a diagram. So you have two VPCs. Each VPC has one instance inside. And when I set up a Bpc peering connection, these two instances talk to each other as if they were all in one VPC. And Bpc peering allows for different AWS accounts and different regions as well. So both of these VPCs can be in different regions and different AWS accounts. And I should also emphasize that one VPC only belongs to one region. You can't have a VPC which spans regions. So if you wanted to have services in different regions which talk to each other, then Bpc peering might be an option for that. And one final thing to note is that packets in the Bpc peering connection, they never leave AWS, so they never go into the internet. There are some downsides with Bpc peering, however. So one downside is VPCs cannot have overlapping CIDR blocks. What that basically means is that the IP addresses of the instances can't be the same. So when I go back here, you can see these instances have different IP addresses, 10.0.04 and 172.31.08. And also each VPC has a different IP address space. You can see these two numbers are different. They can't have the same number. If they did, you couldn't set up a VPC peering connection. So that means that managing a lot of VPCs can get complicated, as you need to kind of make sure that there aren't any clashes in IP addresses. And the second disadvantage is that there's no transitive peering. So what that means is that if you look at this diagram here, we have three VPCs, and there's a peering connection between B and A and C. Well, B cannot communicate with C directly. It can only communicate with A directly. If you wanted B to connect with C, we need a separate peering connection here. So when you have lots of VPCs, again, this can get really complex. So there is another way to set up connections between VPCs. It's something called Aws Transit Gateway. And this diagram pretty much shows how that works. You have VPC, 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 and you can take a transit gateway and you can connect all of these together. And it works not only for VPCs, but also for on-premises networks. And this is what Slack did. So this is how Slack decided to connect their services together using Transit Gateway. Okay, so that's enough about kind of background of how Slack is built. So let's have a look at the outage now. So our story begins at 6 a.m. Or 3 p.m. London time. So at 6 a.m., we started to notice some packet loss between the backend services, to emphasize, in separate VPCs, right? So there is some packet loss happening. That means that not all requests are arriving at the destination, and conversely, not all responses are coming back. Slack are not notified of this yet. So fast forward half an hour, we're at 6:30 a.m. We start to see the first errors showing up in the backend services due to this packet loss. Slack is not notified yet. And it's important to remember that this is Monday, January 4th. So for many, this is the first working day after the holidays. And what that means is that all the caches are empty, and any caches are empty. So in turn, that means that the backend services are experiencing more loads than usual because there's no caches to kind of relieve the traffic, or load rather, should I say. Okay, so we're going to go forwards to 6:46 a.m. So that's 46 minutes since the first packet losses. And this is where Slack were actually notified. They saw notified because of the errors happening in the backend services. So the first thing they did was they tried to roll back the latest changes, which is always what you should do if, well, almost always what you should do if you start seeing errors in production, just roll back the latest changes. But that unfortunately made no difference. Number of hanging requests was increasing. And what's more, very soon after this time, the dashboard and alerting service went down. So in order to, they couldn't see what was going on anymore. So in order to try and diagnose a problem, developers had to actually SSH into the production instances. And this is an artist's rendition of how that might have looked like. So yeah, so they were in the production instances. They're trying to debug or diagnose the issue. We're at 6:57 a.m. now, 57 minutes after the first packet losses, and notice that the Slack message failure rate at this time was still only 1%. So 1% or 99% of messages were going through, which sounds like a lot, but actually, when you think about it, it's not a lot at all, because we expect every message to get through, not 99 and 100. That's way too low. So Slack is kind of down, but it's still up, but 1% is actually quite bad. Okay, so at 7 a.m. Now, what usually happens at 7 a.m.? Well, in this case, all the 7 a.m. Slack reminders around the world kicked in. Obviously, whenever people create reminders, it's always like on the hour, unless someone, is quite smart and decides to reduce the load. But usually people do 7 a.m. Like on the hour reminders. And all these reminders at the same time, they increased the load on the backend server, which yielded even bigger rates of packet loss. And this actually saturated the backend server completely. So all incoming requests were blocked. And so Slack is down. Now let's talk a bit about auto scaling. So, when I've been referring to backend services here, Slack don't make it clear which backend services exactly. So I'm just going to talk like in the generic terms. I'm sure that the web app backend, which makes the kind of first response, was involved. But I'm going to talk about like the services in general. So just imagine kind of instances which are required to take incoming requests and which are required for Slack to work. AWS has something called auto scaling. So that's where you can tell AWS to listen to some metrics on the instances and then to kind of increase the number of instances or reduce the number of instances based on these metrics. So the metrics that Slack used are CPU usage and the utilization of available worker threads. Basically, every instance can take in like a certain number of requests at the same time. So this is what that is. So if AWS sees the CPU usage go up, it's like 80%, then it'll start to auto scale and increase the number of instances. If the CPU goes down, it's like 10%, then they'll reduce the number of instances. And Slack had this set up, and almost every kind of company has this kind of thing set up. So let's think about what's happening. So the backend servers are waiting for responses. So CPU usage is low. And this caused the downscaling to kick in. This is bad for a number of reasons, but one of the kind of reasons is that many engineers were, connected via SSH and suddenly had their connection killed because the instance just went down. So they quickly disabled that downscaling. But very quickly, what happened was that the utilization, this other metric, this utilization of available worker threads went up. And so upscaling kicked in. And when I say kicked in, I mean it really kicked in. It tries to create 1,200 instances in 15 minutes, which is much more than is required during peak load for Slack, as they admit that themselves in the report. So 15 minutes after 7, we have these 1,200 new instances. Now, here is where it gets a bit interesting. So Slack has a slightly unorthodox way of deploying new instances. The instances are created by AWS, but then to actually get the instances online, there's a separate service called the provision service, which configures the instances after they've been created. Now, this provision service had trouble communicating with all these new instances, partly because of the packet loss problem, but partly also because there are so many new instances that the service was hitting AWS quota limits. It's also important to remember that this provision service is like a service, so it's in a separate VPC, probably from the instances that are created, from where the instances are. And what this meant was that most instances were misconfigured and broken. Most of those 1,200 instances misconfigured so that it just didn't work. So engineers had to manually go through and remove these. But then what happened was that the provision service itself suddenly went down. It stopped provisioning. So the broken instances were removed, but no new instances could be configured. This happened at 7:15. As this is, not being able to create new instances is pretty bad. And so we're at 7:15, and now we fast forward 50 minutes. And it's only after 50 minutes that the engineers have found why the provision service had failed. And the reason it had failed was that it had hit the open file handle limit. So every system has a limit to how many open files you can have. And clearly this provision service, while it was trying to configure an instance, it maybe opened up a file while it was configuring, maybe more than one file. And because there were so many new instances, there were lots of open files, and maybe they weren't closing properly because of the network issue. And so they hit the open file handle limit. So they tried to, when they noticed this, they quickly increased the limit. And 10 minutes later, the provisioning service actually recovered. So they were now at 9:15 a.m., so like an hour after the provision service had recovered. And the Slack team had to they deployed some new instances, which worked, and they were able to get enough healthy instances back for service to return. So Slack is back up, but kind of, because the packets are still being dropped. So the issue that started at the beginning was still there. There was still packet loss happening. And it turned out the AWS engineers, they noticed in their internal monitoring that the Aws Transit Gateway had not scaled up properly with the load. And this is why they would have the packet losses. So they manually increased the bandwidth, and that took until 10:40 a.m., so 1.5 hours. At 10:40 a.m., Slack was fully operational. So to summarize, 6 a.m. first packet losses. We get a downscaling in instances as CPU utilization goes down. But then once that is disabled, suddenly there's an upscale due to the worker thread utilization. And that upscale overloads the provision service. And so during that time, while the provision service is down, Slack is down. And ultimately, when the open file handle limit is raised, provision service recovers, Slack begins to recover, and 9:15 a.m. we sort of get back to a semi-working Slack. So who is to blame here? Is it Slack or is it AWS? Well, here's a fact. The AWS Transit Gateway fails to scale up properly because of a problem in the algorithm. So I do not think you can make a case that AWS can blame Slack really for failing Transit Gateway. But the fact is, AWS have on their website written that it's an elastic service. It scales up with load, but it just fails to do that properly at this time. That said, though, could Slack have prevented the outage? Now, this is all kind of, I'm going to go through a couple of maybe kind of points of interest. But this is all kind of hypothetical, of course, because unless we actually see what's going on, what the actual architecture at the time, it's quite hard to say whether this could have been prevented. But these kind of 3 points I kind of came across on various forums and decided to kind of probably interesting to look into them a bit. So the first point, someone might say, Slack did not monitor the health of AWS Transit Gateway. Remember, Slack did not even know packets were dropping until AWS notified them. All they saw was that there were errors happening, and they thought this was a problem with their own app. They didn't actually think. Maybe they did think, but it wasn't like on their priority list. I think to think about that, the Transit Gateway might not be working, actually, might not have scaled up properly. But had they known that packet losses were happening and that the Transit Gateway wasn't working properly, they might have been able to stay at 1% failure rates rather than 100% failure rates. But the fact is that the metrics, so like the status metrics for Transit Gateway are not very detailed. And is it Slack's responsibility anyway to monitor the health of an AWS service? I mean, I would argue not really. Not their responsibility, but maybe good to do. But obviously, in the hindsight, this is you can say whatever you want in hindsight. But I can understand them not setting up an alert for Transit Gateway. So a second point. Slack should not have relied on Transit Gateway to communicate between services. Now, this is something I can maybe sort of understand. AWS do have something called shared VPCs. And this is where one AWS account creates a big VPC, and then it shares portions of that VPC to other AWS accounts. And with that setup, you can segregate services into different AWS accounts. And that's, of course, very helpful. Kind of just from a managerial perspective, and probably one of the main reasons why Slack decides to segregate their services in the first place. Only Slack did segregate it into different VPCs, whereas maybe they could have gotten away with just segregating based on AWS accounts, but having all the services still in one large VPC, and then they wouldn't have had to rely on the Transit Gateway. So that's the kind of second point. And the third point is Slack's auto-scaling metrics were off. So they were measuring the CPU utilization and work with thread utilization, but not the request queue depth. So not the number of requests that were in the queue. Had they seen that it was like there was just one request in the queue, which was timing out and which was hanging, then they might have known that this is a problem with the network, and that's increasing the number of instances is not always. Well, it kind of solves some problems, but not all problems. And the real problem is with the network, not with the incoming load or anything like that. But I think so. These are kind of 3 points. But I think in hindsight, it's very well and good to be able to say, "Oh, I should have done that. Should have done that. Should have done that." I think the bottom line is there's a saying. Saying is the cloud is just someone else's computer, and I think that's very true. I think it's important to always keep in mind that anything can go wrong when you're on the clouds. Literally anything can go wrong, and sometimes it's almost impossible to plan for every single thing that can go wrong. In hindsight, it's clear. We now know Transit Gateway doesn't always scale up properly. But I mean, yeah, it's quite hard to justify before Transit Gateway goes down, to prepare everything in case Transit Gateway goes down. Maybe that's what should have been done, but I'm sure Slack had so much on their plate, they couldn't think about every single thing that might go wrong. But I think the general lesson is just keep in mind, cloud is just someone else's computer, and so stuff can go wrong. But yeah, I think that's the end of presentation. So does anyone have any questions?
Thanks, Tom. I found that very enjoyable. I guess, yeah, does anybody have any questions for Tom?
I've got one, Tom, and I'm not sure whether it's one you'll be able to answer, but let's give it a go. So at Lambert Labs, one of the decisions that we have to take architecturally when sometimes working with clients' products is that if they're selling that product as an enterprise application to bigger companies, let's say, then there's always a decision about whether they want to do multiple deployments of that product across different AWS accounts entirely, for example, or whether they do multiple deployments of their product inside one AWS account, perhaps separated into different VPCs. And I wonder, from what you read on Slack, do they give any indication about what they do in their architecture? I mean, I don't know I don't know everything about Slack's pricing plan, but they've got a free tier for, that lots of organizations will use. They've then got a paid tier, which I think we're on. I mean, I assume that they have some kind of enterprise deployments as well. And I wonder if, do you know if that all runs, at the enterprise deployment level? Do you get your own AWS account? And did those go down? I don't know.
Yeah, it's not clear. There's not much I can say on that, really. I mean, what Slack do, one example of what Slack do is they have something called data residency. So you can tell Slack where you want your data to be stored. So that implies that they their services are in different regions, and that implies that at least the database, I don't know about the other services, but that they are kind of segregated into different deployments. Yeah, I don't know exactly. I think from the reports, they seem to favor like VPC segregation, not just AWS account segregation, but yeah, VPC segregation. So
okay,
yeah,
that's good. Cheers, Tom.
Thanks, Tom. And yeah, thank you once again for your presentation.
Yeah, no worries. Thanks, everyone.